viewers, welcome to the lecture series of algorithms. Today's topic of lecture is analysis of algorithms. Myself, Dr. Preeti Jagmani, I am from Department of Computer Science, Arabic College, University of Delhi. So, you can say in the asymptotic, we are taking analysis of algorithms as today's topic, and we will be completely focusing on asymptotic analysis and its details. So, asymptotic analysis, just as a quick recap, I can say it is the available best way of analyzing algorithms, which depends on input, and it is independent of machine configuration or any programming language. But yes, a valid side effect or a valid criticism of asymptotic analysis is it is valid only for, or it is being considered only for large inputs. But the beauty here is we need not to explicitly implement the algorithm, and we will judge the efficiency just by looking at the order of growth, that how slowly or how fastly the function is growing as compared to its size of input. So, if I am saying order of growth, so order of growth here is a way of having some abstraction flavor into the analysis, which says that we are interested in rate of growth or order of growth of the algorithm, which allows us to compare the algorithm without the implementation performance or without looking into the discrete unit of times, and we are only interested in higher order terms without worrying about the lower order terms or without worrying about the constant coefficients also. But we can say that imagine a situation that we are having a problem of linear search, let us say. So, linear search says that your for the same input size, but with different input configuration, there can be different behavior of algorithms. For example, if you have a particular configuration set in which you are looking for a number, if you are going to find that number on the first place, your algorithm is obviously going to be going to give you a different efficiency. If that particular number which you are looking for is not present, and your algorithm will obviously, if it is correct, and I am assuming that algorithm correctness is the basic thing which we need to have here. So, a correct algorithm will look for each and every number, compare it with your key element, and then say your element which you are looking for is not available, or maybe you can say your algorithm is going to find that particular number or key item, that item is available in the middle, in the, you can say somewhere in the mid of the element, somewhere at the middle location of your array. So, with different with the same input size, but with different configurations, your algorithm may behave differently. So, in one situation, if I am saying my element is found at the first place, it is behaving, you can say, in the best way, and the worst could be if it is comparing with all the n elements, and it is not able to find the element because the element is not available, or another even average case performance could be element is somewhere in between. So, different behavior of algorithms could be, these behaviors are best case performances, worst case performances, or average case performances, which says that time required by an algorithm falls under three types. Best case, which says the minimum time required for the program execution. Average case says obviously the average time required for the program execution, and the worst case says maximum time is required for the program execution. In the linear search, let us consider an example of an array having some numbers as shown on the screen, 34, 67, 98, 2, 4 and some numbers. Now, let us say we are looking for the term 34. Obviously, it is find in you will be able to find it in one comparison, one shot, and let us say we are looking for the term 19, it is not found in any comparison, and let us say we are looking for the term 4, you will find it in fifth comparison. So, fine, there can be worst cases, there can be best cases, or there can be average cases, and all these best case, worst case and average cases are actually your configuration dependent, that how your input set is being configured. So, worst case says that we need to calculate a highest bound or an upper bound on the running time of an algorithm, which is actually, you can say in a layman terminology, that is the maximum possible time taken by an algorithm for a particular specific configuration or for any configuration, you can say, and this is going to give you maximum number of operations to be executed. If such a scenario comes up, that is the worst case. As in the example of linear search, we can say the worst case is when your number is not present. Now, coming up to average case says we are taking all the possible inputs, calculating the computing time for all the inputs, and we are averaging them out. So, basically it depends on distribution of cases. So, when I say it depends on distribution of cases, that means I am assuming here that all the cases are uniformly distributed, which also includes the case of element not present in array in case of a linear search problem, and then we will be averaging out it by n plus 1. So, what is happening here? If I am saying that all the cases are uniformly distributed, that means some kind of probability is involved here. And please be very specific about this, that if I am talking about the term asymptotic analysis, that includes your probability into it, and that is what the difference comes between asymptotic analysis and the amortized analysis. Amortized analysis does not include any type of probability, while your asymptotic analysis do includes probability. Then if I am talking about the best case that means minimum number of operations in order to complete an algorithm or in order to generate a particular output. We must know all the cases that cause the minimum number of operations to be executed. For example, in linear search, the element is present in the kind of, you can say, first position or on the second position also, say you can say. So, best case is basically the minimum amount of running time an algorithm may exhibit. That is what you call best case. This is what the fundamental of best case, worst case and average cases. Now, if I am talking about asymptotic notations, in order to represent time complexity of algorithms for asymptotic analysis, we will be taking help of some commonly used notations, which are big omega, big O and big theta. Although there are some small omega and small or all the other notations are also possible, but these three, big omega, big O and big theta, which are commonly known as omega or big O and theta, are very frequently and commonly used. So, let us explore these big omega and theta and big O notations one by one. Coming to big omega. So, big omega gives first of all, it is the least used notation among all the three notations which we are considering. It is giving you a lower bound on the time complexity of algorithm, and if I am saying lower bound, that means I am implicitly, or I mean here is asymptotic lower bound. For example, in case of linear search, if I am say this is possible for an arbitrary input when elements to be searched can be found at the first position. So, the lowest bound or the minimum possible time a linear search can take will be omega of constant 1 in terms of mathematical notations of asymptotic analysis. We take 1 is obviously as a constant, and if we want to represent constant, we represent it by 1. So, omega of 1 is going to give me the lowest bound for linear search. Coming to the technical definition of big omega, you can see a figure on the screen in which I am having two curves. One is represent f of n, another one is representing g of n along with a multiplication of a constant. And on the x axis, please notice that on the x axis we are having n, and on the y axis we are having time. So, what we are which part of graph we are looking into is very important here. We are just focusing, as we have seen in asymptotic analysis, that we will be focusing on large enough inputs. So, we are focusing on the part of the figure or part of the graph where it is going to cross the limit of n0. That means, we will be looking in the right portion of the graph where n is greater than n0. So, coming to the technical definition, I can say I am having a function gn which is denoted by omega of gn, and there exists a set of functions f of n for which positive constants c and n0 such that I am having all the values of f of n are greater than is equals to the values of g of n multiplied by the constant c. And what I am talking about, that all the values should be greater than 0. That means, here I am talking about all positive values of f of n. That means, now your c multiplied, where c is a constant, c multiplied by g of n is less than is equals to f of n, and 0 is less than is equals to c of g of n. That means, and what it is for all n greater than n0. So, basically here theta of gn is f of n. That means, we are going to have we are going to claim the least amount of time which algorithm is going to take. Here we are not talking about the maximum amount of time, or we are not talking about the upper bound of the time. So, here least amount of time which will be taken by algorithm is c, which is a constant, multiplied by g of n. So, here omega of g of n is f of n with all those n and n greater than n0. So, basically what I am trying to say, this is like making a claim here that one is having at least 50 rupees in his or her wallet when they really have 10,000 rupees, and if they are saying that we are having at least 50 rupees, that means claim is true enough. But what we are talking about is, we are talking about the least amount of money that they are sure about, although they are having 10,000 rupees. That means, the least amount of money is 50 rupees which they are claiming that they have, but they really have 10,000, less than 50 they can't have. So, 50 here is, you can say, is a lower bound here. So, similar in this way we are having the big omega as the lower bound of any running algorithm. Now, if I am saying that I am having 50 rupees, or if one is saying that he or she is having 50 rupees, that statement is quite correct, but it is too imprecise. Or similarly, we can say that worst case running time of linear search is omega 1, because it is sure that it takes at least constant time, it is going to take. Then we can say worst case running time is going to be the omega 1. It is, statement is quite correct, but statement is too imprecise. So, correctly but not precisely. We can say worst case running time of linear search is omega 1. That means we are talking about the minimum possible time which linear search must be taking. We are not talking about any upper bound it may take. So, if I am talking about next the term big O. So, big O, as big omega has given the has bounded the algorithm efficiency by below, big O is going to give me an upper bound of the algorithm. That means it bounds a function only from the above, and we always use big O notation when we have an upper bound on time complexity of the algorithm. Generally we use big O, we do not use big omega, because of the simple reasons that we are actually interested in the upper sides only, because we it is not good to make false promises in terms of your algorithm efficiency or in terms of your software efficiency. So, it is better to be on safer side, and in any case your life is brutal. That means we cannot expect our input size or your input configuration to be kind enough to us to have a particular least to have a least amount of time to be executed. So, we are always interested in upper higher notations like big O, and then this big O can be simply found by looking at the algorithm with some practice. Now, as we have seen in case of big omega, that the function was bounded below. If you can notice the difference between that particular graph and the graph here which is shown on the screen, you can see the reverse position of Fn and Gn. So, here one can very well understand that again we are talking about the all the values of n greater than n0, and then what we are interested, that function Fn which represents the time of time complexity of our algorithm is bounded above by C of Gn. That means whatever time our function Fn or whatever time our algorithm is going to going to take to be implemented, that will always be lesser than C of Gn for all values of n0 greater than n. That means the running time grows at most to C of Gn, but it could grow more slowly. So, basically I can say it is a blanket statement that is going to cover all the classes. And in terms of technical definition, I can say big O of Gn is a function such that there exist positive constant C and n0 such that your 0 less than equals to f of n less than equals to C multiplied by Gn for all values of n which are greater than n0. That means how whatever value by which your algorithm time grows up, it is going to be lesser than C of Gn. That means you can say in a kind of layman terminology that your C of Gn is the blanket, that your f of n will grow at most to the C of Gn, but it could grow more slowly also. So, it will not grow more than C of Gn. So, C of Gn is a kind of upper bound on the function of efficiency of the algorithm or function of the running time of algorithm. So, big O notation gives only the asymptotic upper bound, as your big omega gives only the asymptotic lower bound, but again both are not tight bounds. Big O is going to give you asymptotic upper bound, big omega is going to give me asymptotic lower bound. They are not tight bounds. Big O bounds the growth of running time from above, big omega bounds the growth of running time from below. For example, in case of linear search, I can say big O of linear search is order n. That means the linear search algorithm can take time at most of order n. For example, there are, let us say, 20 or maybe 20,000 elements. So, comparing each and every element, it is going to take time equivalent to some discrete units of times of 20,000 for each one for each comparison, and it may or may not find the element. If it is present, it may find it. If it is not present, it may not find it. So, we can say running time grows no faster than a constant times n. In fact, it may grow slower in case of a linear search. This is like making a claim that one is having less than 10,000 rupees in his or her wallet when the money available is 50 rupees only. Money available here is only 50 rupees, but I can say yes, it is less than 10,000, that means I am sure. So, 10,000 rupees here comes as a blanket statement that I am having less than 10,000. It is not going to be more than 10,000 in any case, but the actual money available is 50 rupees only. So, you can say claim is absolutely correct, but it is horribly imprecise also, because there is a huge difference between what actual money you are having and what bound you are claiming. So, here these type of differences can grow in terms of big O notations, that there is some f of n and what g of n you are claiming is going to be very higher than that. Your statement will be correct, but it is going to be horribly imprecise, in the sense that let us say I am having a function which is of let us say a n square plus b n. So, I can easily say it is n order of n square, but if it is I am saying it is order of n to the power 4, fine. If I am talking about big O, I am talking about the upper bound. Upper bound could be order of n 4 also, but there is a huge difference between order of n square and order of n 4. So, again your claim is absolutely correct, but it is too imprecise. Now, the next notation is big theta. So, theta notation is basically a tight bound, I can say. It is actually class which is bounding the runtime, which is bounding the function f n from above as well as from below both. So, it is going to define the exact asymptotic behavior, a tight bound. So, a definition of theta as the definition of omega and O requires f n to be non-negative for all values of n greater than n0. If I am talking about in terms of asymptotic analysis, your f n or your running time should not be negative in whatever cases you are talking about. So, for theta, you can see that particular graph on figure on screen. So, f of n here is theta of g n. So, you can see your f of n is actually covered, or I can say sandwiched between C2 Gn, where C2 is a constant and where C1 is also constant. So, your Fn is covered, or it is lying between, or it is blanketed between C2 of Gn and C1 of Gn, where C1 and C2 are two constant. So, for a given function Gn, we denote theta of Gn is a set of functions such that there exist positive constants. Now, here are two constants C1, C2 and the third constant is n0, such that all values you are having positive. So, your Fn is sandwiched between C1 Gn and C2 Gn, which is mathematically you can say C1 multiplied by Gn less than is equals to Fn less than is equals to C2 multiplied by Gn. And yes, obviously for all values, all higher inputs we are talking about, which where n is greater than n0. So, I can say the above definition, the meaning of the above definition is Fn is the theta of Gn, then the value of Fn is always lie between C1 Gn and C2 Gn. So, here a class has been defined, a particular interval you can say is being defined, the class or the interval of the functions which is lying between C1 Gn and C2 Gn will represent the complexity or will represent the runtime efficiency of the algorithm. So, theta if Fn automatically implies big O of Fn and big omega of Fn, as it is including the upper bound as well as the lower bound both. So, once we can say once n gets large enough, the running time is at least C1 Gn and at most C2 Gn. The running time will lie between these two limits. It is not going to be less than C1 Gn, it is not going to be more than C2 Gn, it is going to lie, it is sandwiched between these two terms as long as your constant C1 and C2 exist. So, your asymptotically tight bound, which is theta, is bounding the running time to within a constant factor by above or by below, both you can say. So, coming to, if I am saying worst case analysis or the best case analysis, worst case analysis means least amount of resources when needed by algorithm, that is your best case, and it is achieving when you are considering the sorting example of sorting, let us say insertion sort, achieved when incoming list is already sorted in increasing order. If you can recall the pseudocode of insertion sort, it is having two loops within two nested loops, I can say, one within the another. So, second loop, which is for comparison, is never iterated, it is never entered into. So, the best case will be your algorithm will run in linear amount of time of n. So, that means your runtime is a linear function of n. And coming to the worst case, when your incoming list for insertion sort is in the reverse order, arranged in the reverse order, that means if you are looking for an output list in the increasing order, the input list is already arranged in the decreasing order. So, here the second loop, which is the inner loop, will be iterated for each and every time, which is maximum number of times, and your time will end up as a quadratic function of n. So, for practical analysis point of view, we can say worst case is going to provide an upper bound on running time, which is an absolute guarantee. Average case is basically dependent upon the expected running time, as I already told you that probability here is involved, and it rely on random, which are equally likely inputs. So, for the most part, what we are interested is in running time, worst case running time, which is you can say we are interested in the upper bound for any input, or average case analysis also done sometimes, but best case analysis we can say, or the best case run time, we are not actually interested into, because that is you kind of giving such false promises, because your input may not fall into the category of best input or best configuration input every time. So, technically we are interested into worst case analysis of algorithms. Hope you have enjoyed the lecture. Thank you.